Go. Welcome, everybody. Let's get this focused. I believe this is lecture 8, and if it's wrong, I'll fix it later. We are starting chapter 5 of the Baymard, and this is also chapter 5 of the OpenStax textbook. And the topic is continuous probability distributions. The second type of probability distributions we study in this class. So we've talked about discrete probability distributions. A discrete probability distribution has outcomes that can take specific values. What's my recommendation for the best way of looking at a discrete probability distribution? Yeah? Sorry. Exactly, a frequency table, right? So a frequency table, I think it's technically a relative frequency table because they're probabilities, right? So a relative frequency table is how we present discrete probability distributions. And that makes sense because a table is good when you have a limited set of specific values. Doesn't work so well for a continuous probability distribution. A continuous probability distribution has outcomes that can take any value in a range. I explained this to my Math 95 class as imagine you have pancakes. Who here prefers blueberries on your pancakes versus chocolate chips? Okay, so a discrete probability distribution is like chocolate chips on your pancakes. They're individual chocolate chips. A continuous probability distribution is like pouring syrup on your pancakes. You've got this nice spread of syrup that covers that whole range. If that helps you think about the difference. Also, if you ever take another math class, that might come up as well, and I find that to be a useful analogy. Tables don't work super well when you can take any value in a range because that's an infinite set of values. Not only can you be 1 or 2 or 3, you could also be 1.5 or 2 1/3 or 1.987634205. Were you thinking the number 5? No, it was just a guess. I had a 1 in a 10 chance, assuming you were thinking of a number at all. So instead of using a table, we use a graph called I call it a density function. But in particular, we use a graph. That's the type of visual we use. Focus. Thank you. So let's look at an example. We'll let x be a random variable whose probability distribution can be described by the following graph. I'm going to draw it first and then we'll start talking about it. It's like that. You can draw something like that. It doesn't have to be exactly that. Sorry, there's units on there. Pull the, there. So the first question you might ask is, I notice you don't have units on the height. So what does the height of the graph tell you? The height of the graph, it's not exactly the probability, but for now you can think of it as a measure of probability. The technical word is density. But parts of the graph that are higher are more likely than parts of the graph that are lower. So it indicates probability. What's the minimum possible value of X I could imagine getting? Any ideas? 2. Yep. I should have put here, this is the value of X. Put that right in the middle, right? X-axis. The minimum possible value of X I would ever expect to get is 2, because the graph doesn't live anywhere to the left of 2. And the maximal possible value? Yep. Of X is 12. So already from this picture, I can say this is a continuous random variable that takes values between 2 and 12. I'm going to redraw it on the next page. These graphs get cluttered really quickly. So I'm going to just kind of keep redrawing it. It'll change just a little bit every time I draw it because I can't make it exactly the same. But pretend that it's basically the same. Here we go. Same graph. Two, 4, 6, 8, 10, 12. Something like that. Pretty close. Okay. In a discrete probability distribution, we listed the probabilities in our frequency table. In a continuous probability distribution, probabilities are areas. You read off the probability by looking at an area. So I should have gone ahead and gotten better units. This is 4.5, and this is 6.5. Yeah. So I would say that the probability of observing X between, we just say the probability that X is between 4.5 and 6.5 is the area of area under curve or the line, the graph between (4.5) and 6.5. And mathematically, we would write it as probability that x is between 4.5 and 6.5, like that. This is both very important and very useful because you can read off a probability just by looking at an area. Now, it can be hard to calculate what that area is. So we have a couple tools for that. But the concept is the key idea, is the probability is an area. Same graph again. You can redraw it or not. That's up to you. You can just keep using the same one as reference if you want. 4, 6, 8. Okay. Let's look at what does this area represent? Talk about it with your neighbor. Take a minute. Talk about what that shaded area represents. Someone want to venture a guess? That's exactly right. So this shaded area is the probability that x, is between 4 and 6. Right? And then that would mean that this area is a probability that x is between 9 and 11. Which of those is bigger? Which probability is bigger? Take a minute, talk about it with your neighbor. Which of these probabilities is, what's a probability again in a continuous probability distribution? Should be in your notes.
The area to one number to another.
Yeah, a probability is an area. So which of these probabilities is bigger? The 4 to x, or 4 to 6, or the 9 to 11? Why do you say 9 to 11? Because the area is bigger. Yep. Yeah. So the probability between 4 and 6 is less than the probability of being between 9 and 11 because the area under the curve between 4 and 6 is smaller than the area between 9 and 11. And that's how you figure out probabilities or compare probabilities with a continuous distribution. You literally just look at the areas. Okay. How would I know the probability of being between 4 and 6 or being between 9 and 11? How would I know that? Yeah. Yeah, I mean, even if I don't care about the specific number, but if I want to visualize the probability of between 4 and 6 or 9 and 11. I'm asking a slightly different question. I'm saying, what's the probability of being in this range or in this range? Mm-hmm. Exactly. I'd add up the areas, right? Add the two areas together. That gives me the probability of being in this one or this one. Yeah. So far, we're really not putting any numbers on this, right? We're just talking about areas in a very conceptual way. Let's go ahead and put a number on this. What is the total area under this curve? Take a minute, talk about it with your neighbor. See if you can figure out what the total area is under this curve. So what is the total area under this curve? 100%, or in probability terms, 1. Because we always know with a probability distribution, the total probability is 1 because something has to happen. The total area under this curve, in fact, for any probability curve, equals 1. And this is true for any probability curve. And that is often why we don't put a vertical scale. The vertical is less important than the area, right? If I were to put a vertical scale on here, I'd have this top point would have to be the right amount so that area ends up at 1, which is 10. And I gotta do some thinking here. That's about 1. So I would make like this height a 1/10, which is kind of meaningless. So we usually don't care too much about the vertical scale. What we care is that the total area under any probability curve always equals 1. All right. How about another question? I'm going to draw the same graph. I'll ask you a couple questions. Some of the questions are going to be the exact same questions because it never hurts to do the same questions over and over again. Okay, so the probability that, let me just put some numbers down. The probability that x is between 4 and 6 compared to the probability that x is between 9 and 11. Which of these probabilities is bigger? Right, and the reason is the area is larger. Okay, so I could do this. Okay, the total probability equals what? 100%, or 1, which is the total area. Talk about with your neighbor, what's the probability that x is exactly equal to 5? And this is a probability that x equals 5. There is a number. You can figure it out. Talk about it with your neighbor. See if you can figure it out. So let's change that. How do we measure probabilities with continuous probability distributions? Area. So this is the area under the curve when x equals 5. So how do I draw the area under the curve when x equals 5? Give that a shot. Try to sketch it in on your paper, especially if you have a pencil so you can erase it if you need to. What does it look like when we sketch the area under the curve for x exactly equal to 5? What do you think, Bella? Exactly. It's a line right there. What's the area of a line? A line is a one-dimensional object. What's the area of a one-dimensional object?
1%.
Not even 1%, less than that. Even less than that. 0. The area of a line is 0. A one-dimensional object, by definition, right? Two-dimensional objects have area because you have a length and a width. One-dimensional objects, by definition, do not have area. So the probability that x equals 5 is the area of the line at x equals 5, which is 0 for any specific value, not just for x equals 5. What's the probability that x equals 6? Exactly 6. The same, so 0. What's the probability that x equals exactly 9? What's the probability that x equals exactly 10.3? 0. So the weird thing about a continuous probability distribution is the probability of any specific value is actually 0. If we imagine these are, I don't know, weights of cats, let's say, this is a probability distribution for the weight of cats. Is it impossible for a cat to weigh exactly 5 pounds? It's not impossible. It's not impossible for a cat to weigh exactly 8 pounds. So saying something that has probability 0 is not the same as saying something is impossible. It just means the probability is 0. That's super weird, right? This is not the same as saying something is impossible. So there's a difference between mathematical probability and what we normally think of as probability. It's kind of related a little bit to the idea that there's always a chance, but even so, it's not really that either. It's just keep in mind it's weird. This one is a place where it gets a little weird. The probability of anything happening, any specific value is 0, which is not to say it's impossible. Okay. What comes next? I just had it. Okay, this is different from a discrete probability distribution. Let's look at an example. Roll 1 die, which is the singular of dice, and let x be the value. Is that discrete or is that continuous? Because can you ever roll a 3.7? No, right? It gives you specific values that you can take. What's the probability that x equals 5? And that's a number, you can figure it out. It's 1 out of 6, right? It's not 0 because it's basically because it's discrete, right? So continuous probability distributions have a probability 0 for a specific value, but discrete ones don't. I'm going to put this in a little bracket. This is also why we prefer ranges when doing statistics. If we're looking for extreme values, we don't look for a specific value. We say for something above that value, for that range above the value. And we'll come back to this again and again, especially when we start doing hypothesis tests in a couple of weeks. But one reason we prefer talking about ranges instead of specific values is because of this idea of continuous probability. Okay. All right, so let's talk about two types of continuous probability distributions that are used pretty frequently. They're the two that we'll study in this class. So the first one is called a uniform distribution. And this is a probability distribution where every range, or I should say, instead of range, I'm going to use the word interval, which basically means the same thing, but it's more mathematically precise. Every interval of the same length has the same probability. And with that definition, we can actually draw what a uniform distribution looks like. So let's do an example. Let's start at 3 this time. And let's go up to 15. So if every interval of the same length has the same probability, then an interval that's this long, right there, has the same probability no matter where it is. So I'd have to put it anywhere. And when I do this, what do I end up with? A flat line that goes between the minimum and the maximum. And that's what a uniform distribution looks like. It's a flat line that goes between the minimum and the maximum. What's the total area? 1. Yep. That actually tells us how high it has to be. This interval is 12 units long. So the height has to be 1/12. So unlike many continuous distributions, we can actually figure out the vertical scale pretty easily. Let me move this total area here. Let's look at this area. That's the area between 6 and, looks like 6 and 9. The probability that x is between 6 and 9, well, since it's a rectangle, it's a pretty easy calculation. All I have to do is say, well, it's this distance, which is 3, divided by the total distance, which is 12. All right, so in particular, it's 9 minus 6 over 15 minus 3. Or if you want to think about it this way, it's b minus a over the total length. where 6 is A and 9 is B. Uniform distributions are useful for two reasons. Actually, let me pause unless you get caught up. Three reasons. Three main reasons. I'm sure there are more that I haven't thought of. First, they're mathematically simple, which is nice. Easy to calculate a probability. It's an arithmetic question. Second, many physical systems can be modeled by a uniform distribution. For example, birthdays. There are 365 or 6 birthdays in a year, which is not uniform. That's discrete. Those are specific days. But it's so close to uniform. Let's just treat it that way. Right? The whole point is a model is never perfect, but it makes it easier to investigate. So birthdays have a lot of possibilities, all of which are equal, more or less. And the probability that someone is born in January is roughly equal to the probability that someone's born in June or October, etc. And so we can model birthdays as a uniform probability distribution. And the third reason is they're useful for simulations. A lot of times when we work with data, we want to generate more data to work with, but we can't go out and collect it. So instead, we simulate our data and we use a uniform distribution to simulate data from the data we already have. All right. Anybody have questions about that? Okay, that's uniform distribution. That's about all we're going to investigate with uniform distribution, some basic probability calculations. The distribution that does all the heavy lifting in statistics is called a normal distribution. The word normal doesn't mean other distributions are weird or abnormal. Normal distribution here means it's a bell curve. When you draw enough, you get pretty good at it. So if yours don't look great, that's all right. If you become a statistician, eventually they'll look real good. The nice thing about bell curves is they're symmetric. So they have a great mean. Here I'm going to use expected value of x for the mean. And bell curves are one of those special distributions where just about 90% of the probability, or another way to put it, 90% of the area, is between two standard deviations. And that's the reason we use two standard deviations so much, is 95% of the area is within two standard deviations of the mean. So 0.95 in terms of probability is within two standard deviations of the mean. Any normal distribution, truly normal distribution, not just an approximation, but any normal distribution is completely described or determined by the mean and the standard deviation. Those are the only two numbers you need. And then mathematically, you can draw what the bell curve looks like. So, for example, someone tell me a number. 7. Okay, so I'm going to have a normal distribution where the expected value or the mean is 7 and the standard deviation is, let's say, 3. Most of the time, your standard deviation is going to be relatively small compared to your mean. It could be bigger, but that would be surprising. So as soon as I have that, I can draw my normal distribution. I always draw the curve first, and then I add in the important pieces. Here's the mean. What's the value of that mean? Yep. And then here's one standard deviation. I drew it really well this time, but even if I didn't, I'd just adjust my scale. All right, so there's 10 and 13 that way, and 4 and 1 that way. All right, where this is one standard deviation, it's 3. Now I can start asking some questions. For example, what's the probability that x is greater than 7 or greater than or equal to? That's a number, and I think you can tell me the number. So talk about it with your neighbor and decide what is the probability of observing an x greater than or equal to 7. So the probability that x is greater than or equal to 7 says I'm going to observe an x that is here or more. And Lily, what was that probability you just said? 50% or 0.5. Yep, because it contains half the area of the shape. Yeah. How about the probability that x is less than, I wrote that weird. Let me do it again. The probability that x is less than 1 or x is greater than 13. So that's the tails. What's the probability that x is in these tails that's more than 2 standard deviations away from the mean?
Less than 5.
Yep. 0.05. 5% or 0.05. It's actually not exactly that, but it's so close that we're good with it. Okay. How about the probability that x is greater than or equal to 11? That's not very easy to tell from a picture, right? The picture gives us more detail than just the summary statistics, but it's hard to get an exact value. So instead, what you can do is, let me find my, you can come down here to week 5. Is it week 5? week 4, because we're still in week 4, and you can click on this app for visualizing normal distributions. And it wants a mean. What did we decide our mean was? Yep, and it wants the standard deviation, which we decided was 3. Let me see if I can zoom in a little bit. Yeah. And there you go, we plotted it. Looks kind of like what I wrote, what I drew. And now I want the probability that X is greater than or equal to 11. 9, this one gives it as percents, so fine. A little more than 9%, 0.09. It also tells me how many standard deviations that is. Remember we talked about a z-score? It tells me that's 1.3 or 1 1/3 standard deviations to the right of the mean. So you put in your 2 parameters that completely describe your curve, you plot it, and then you pick your boundary points. You can do to the right. What's the probability of being less than 11? Talk about it with your neighbor. What do you think, Lily? 91%, because if you're not above, you're below. Yep, just about 91%. You can do between 2 values. So now I get to pick, let's say, well, let's check between 1 and 13. That's within 2 standard deviations of the mean, just about 95%. Tiny bit more, but close enough. Which means, of course, outside of the region from 1 to 13 is just about 5%, which is statistically surprising. That's why 2 standard deviations or more is statistically surprising for normal distributions, because it corresponds to probabilities. Okay, so any question in your homework, for example, let's see if I can find one. Okay, here's one. So Terry Vogel is an amateur motorcycle racer. I don't know if that's true. There's the average speed for Terry Vogel, and there's a standard deviation of the speed for Terry Vogel. So we can see this if we put those quantities in, 129.08 and 2.26. And I got to clear this stuff. It doesn't change the shape. Oh, it hurt. Okay, let's start again. Yeah, sometimes you just got to refresh. The shape looks the exact same. What changes is the scale. But now we can start asking questions about probabilities. Things like, what proportion of her laps are completed between 1.2597 and 1.2757? So that's between 2 values, 125.97 and 127.57. 0.1676 or 16.76%. Right, so this is a really useful tool for your homework. There's a way to simulate this in R. How are you going to do it on your quiz? In fact, I should just post it, but let me show you. How are you going to do it on your quiz? You're going to get have it somewhere. This. Right, where the areas are shown. So I could ask you, for example, here's a question. What's the probability of observing an X between 1 and 2 standard deviations above the mean? And you would say it's 9.2% plus 4.4%. And if I told you the mean was 30 and the standard deviation was 5, then I could say what's the probability of being between 35 and 40, which corresponds to between 1 and 2 standard deviations above the mean. Right, so you're doing the same thought process. I'm just restricted in what boundary points I can ask you because I want you to be able to get the probabilities from the picture instead of from the app. Here I could ask you anything because you can always get it in the app. Let's go back to a different one. Last question, I think, for today. What's the probability of being more than 16? Roughly. Very close to 0. 0.13%, 0.0013. That's 3 standard deviations above. How about 4 standard deviations above? What's the probability?
0.
Effectively 0. But look, that's an approximate. Standard or normal distributions go on forever. Just like Lloyd, there's always a chance. But it's effectively 0 once you get past 3 standard deviations. It's something you wouldn't ever expect to see. So it's true that this could go on forever, but at a certain point, a computer's going to throw up its hands and it's going to say it's basically 0. And as statisticians, we can take that as well. Yeah. All right. That's it for today.